Hey guys, in this video we're going to be looking at two-dimensional momentum collisions. An eagle with mass 4.2 kilograms moving with speed VA equals 7.7 meter per second is on a collision course with a second eagle MB equals 5.5 kilograms moving at VB equals 10.1 meter per second in a direction perpendicular to the first. After they collide, they hold on to one another. In what direction and with what speed are they moving after the collision? All right, so because they stick together, that's why we're only asked for one speed here. This is an example of a perfectly inelastic collision. Okay, so first things first, we're going to draw a picture. Okay, so we've got our mass A. I'm going to draw my eagle as a circle. Okay, this eagle is flying in one direction. Now we know that the other one is in a direction perpendicular to the first. So I'm just going to go ahead and draw the second one like this. So this one is on a collision course heading perpendicular to that one. So this will be MB, and this one here will be MA. Now I also need to set a coordinate axis for this question. So here's what I'm going to do. I'm going to call this direction X, that direction Y. These two will be the positive directions in the two dimensions. Okay, now after the collision, these two hit. I mean, you can imagine it's going to go off something like that, right? They're going to collide and go off like that. The masses are similar, so after collision, okay, let's just draw this axis. After the collision, they might go off something like this. Okay. All right, so that's MA plus MB. Now, what we have to do is figure out what that speed is and what the direction is. So there's going to be some angle there relative to the original direction of MA. Now, the way you solve these two-dimensional collisions problems is by conservation of momentum, just like we did in the previous videos, except because it's two-dimensional, we solve, we don't just do P1 equals P2, we do this in the X direction and in the Y. So we will start off with the X direction, so we're going to do P1X equals P2X, and we're going to do the same thing with the Y. So in the X direction, we say P1X equals P2X. Okay, so originally in the X direction, the only thing that has an X component is MA, right? These two are the P1s. This one is for the P2. So P1, the only thing that has an X component is MA. So P1X is just MA V1A. Finally, we have only one component in the X direction. It's the masses of both of them, and we'll need the X component for that. So mass A plus mass B times V2, we can call it V2AB because they're moving in the same direction, final speed, and it's the X component of that. Okay, so the collective mass and the final speed in both of them in the X direction. Now, we're trying to find V2AB, right? So for this expression, let's solve for V2ABX. So V2ABX, so divide both sides by MA plus MB, you're going to get MA V1A over MA plus MB. Okay, so there's one expression for you right there. Next thing we're going to do is go ahead and do the same thing, but in the Y direction. And as you do more of these problems, you're going to see that the problem-solving strategy is almost the same. Okay, so Y direction, we're going to do P1Y equals P2Y. And there's a lot of symmetry to this problem. You might see a lot of things coming out that look the same. Okay, so initially, between the two of them, only this one, MB, has a Y component. So P1Y is MB V1B. And then finally, the Y component after the collision comes from the Y component of the speed of these two objects stuck together. So it's going to be P2Y is MA plus MB times V2AB subscript Y. Okay, again, I'm going to solve for V2ABY, so divide both sides by MA plus MB. This should look familiar. So V2ABY is equal to MB V1B over MA plus MB. Okay, so now we've got two expressions, one for the X and one for the Y. We know how to solve this. Okay, this is a right angle triangle here we've made. We know how to solve the right angle triangle. Okay, so this is essentially what you're doing. You know, I think I'll do this on a new sheet. Just so, okay, here we go. So this is what you've got. You've got your V2AB, right? Based on the picture, it's going off at an angle. And of course, we can break it up into its X and Y components. So this is V2ABX, and this is V2ABY y. Those two meet at a right angle. Now, I just came up with expressions for both of those, right? They're right here. And notice that for the expressions, we know what these things are. We know MA, we know V1A. That's just a VA up here. MA and B, V1B, we know that's just VB right there. So we know all this stuff. It's just in a different expression. So if you want to do this based on Pythagorean theorem, then to determine the speed, right, the hypotenuse of this right angle triangle, just do Pythagorean theorem. So V2AB is equal to the square root of V2ABX squared plus V2ABY squared. Okay, now I'm going to substitute my expressions for V2ABX, V2ABY, the ones that I just determined on the previous slide. Okay, so put a big square root because the expressions are large. Put brackets in the squares so you don't forget it. Sometimes that is where we make a mistake in physics, unfortunately, just in the math part. So V2ABX is MA V1A over MA plus MB, and then V2ABY MB V1B over MA plus MB. Okay, now take a look at that expression for a second. Remember, when you have a square on a fraction, the square gets applied to both the top and the bottom. Okay, so that square gets applied to the objects on the top and the bottom. Now for the top, because there's two things being multiplied, the square applies to both of them. On the bottom, because it's an expression MA plus MB, the square just gets applied to the outside of that MA plus MB there. Same thing here, the squared gets applied to the outside of the MA plus MB. Now here's the thing, if you've got MA plus MB squared, both denominators are the same. So first thing, you could combine them and make a common denominator. But if it's squared, you're taking the square root. The square root means you take the square root of the numerator and the denominator. So let me show you what I mean. Okay, so first thing, let's just merge these into one denominator. So MA plus MB squared over MA squared V1A squared plus MB squared V1B squared. Okay, this is what I mean. Now, when you take the square root, essentially I'm taking the square root of the numerator and then dividing by the square root of the denominator. That's what it means to have a square root over a fraction. Okay, so in other words, if I have the square root of A over B squared, okay, that's the same thing as square root of A divided by the square root of B squared. But because B squared and square root, those two go against each other, I'm left with square root of A over B. And that's essentially what I'm going to do here. My B squared is the MA plus MB squared in the denominator. I'm going to get rid of that, the square. Okay, so essentially I'm going to be left with MA squared, V1A squared, plus MB squared, V1B squared. And then that radical should only be in the numerator over MA plus MB. Okay. So at this point, you just have to plug in your values so that you can solve for this. Okay, so let's plug in our numbers. So MA is 4.2 kilograms. Remember, that has to be squared. V1A, 7.7 meters per second. Squared plus MB, 5.5 kilograms. Squared plus, times V1B, 10.1 meter per second squared. And all of that gets divided by 4.2 kilograms plus 5.5 kilograms. Pretty much plug this in your calculator. Just be careful when you're doing it. I would suggest do this part first, then this part, add them together, then take the square root, one step at a time. Okay, so when you do that, you are going to end up with, we haven't had a long problem like this in a while. Okay, so when you solve that in the numerator, you should be getting 64.278 kilogram meter per second. And on the denominator, 9.7 kilograms. So you can see that the kilograms are going to cancel out. So you just divide those two numbers and your result is going to be V2AB equals 6.6 meters per second. Okay, so that value makes sense, right? Because you always have to ask yourself in physics, does it make sense? One's going at 7.7, the other's going at 10.1. They collide. The overall speed is going to be a little bit less. So there's the speed. Now we have to find the direction. Okay, so the direction we'll do next Now for the direction, think back to that right angled triangle we drew on the previous page. This thing right here, right? So we've got V2AB made up of its components, x and y. So this is going to be the direction theta with respect to the original direction of the motion of MA. Okay? So that's what we're looking for, theta. So based on the triangle, tan theta, right? So let me just quickly sketch that here again. We've got V2AB, V2ABY, V2ABX, right? So this is my theta. So tan theta, opposite over adjacent, and tan is always y over x, if you remember even like that. So V2ABY over V2ABX. Okay, now plug in your expressions, the one we derived on the initial sheet. Okay, so V2ABY, MB V1B over MA plus MB, all over MA V1A over MA plus MB. Now when you have a fraction over a fraction, if the denominators are the same, they actually cancel out. And the reason for that is, imagine you had 1 over 4 divided by 3 over 4. Okay, so this is the same thing as 1 over 4 times 4 over 3, right? When you bring the fraction in the denominator up to the top, you have to flip it, okay? So therefore you see the 4's cancel and you're left with 1/3. So from this point of view, if you have a fraction divided by a fraction, you cancel out the denominators if they're the same, or you can simplify them and you're left with whatever result you have, 1 over 3, for example. So here, the two denominators are the same, so I can cross them out. Okay, so all I'm left with is MB V1B over MA V1A. Remember, this is tan theta we're solving for. So plug in your values. 5.5 kilograms, 10.1 meter per second, divided by 4.2 kilograms, 7.7 meters per second. Punch that in your calculator, and remember we're solving for tan theta. That number is going to be 1.71769. Okay, so to solve for that, take the inverse tangent of both sides, and we're going to be left with theta is equal to 60 degrees. Now, what is that relative to? Remember, this is relative to the original direction of x, or eagle A. So relative to original direction of eagle A. Okay, so there's your direction, and your speed we solved up here. So those two parts put together give you your final answer. So that's it for this video, guys. I hope you enjoyed it. Be sure to smash that like button if you enjoyed it, and subscribe to Physics in the Flesh so you can stay tuned for my latest videos. Next one being posted tomorrow at 12 noon, video 129, Two-Dimensional Collisions 2. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. As always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.